Hello everyone, welcome back. Today we're going to be talking about chemical kinetics, reaction rates, and we're going to be covering the collision model. Chemical kinetics is the study at which a study of how fast chemical reactions occur. Um, some reactions are fast, others are slow. Um, that's that seems pretty intuitive. Anyways, um, with that said, the way we measure rate is we typically do the difference in molarity over is the change in molarity of a reactant or product per unit time. If A is a particular chemical species, then the rate is delta concentration of A over delta T, which amalgamates to that. Where T2 is later than T1 and A2 is the molarity of A at T2. The rates are usually measured in molar per second, or more formally, that, mole per cubic decimeter per second. It can either be a rate of consumption or production, and reaction rate is generally quoted as a positive value, so you usually just take the rate of production. And reaction rate is defined as the decrease in molarity of products per decrease in molarity of reactants per unit time, or the increase in molarity in products per unit time. Just take the absolute value and you get the reaction rate. And then if you're asked whether it's a rate of consumption or production, you can use your physical reasoning to deduce what it is. And in which both cases, the reaction rate will be positive. And consider this following reaction here, where essentially what it amounts, what you can do is to get the reaction rate, you can either do negative the rate of consumption of nitrogen dioxide, which equals the rate of production of nitrogen monoxide, which equals 2 times the rate of production of oxygen. Note here that these are the mole ratios are met. You see here, this is 2 to 1, so this is 2 to 1. So this is double to equivalent that rate. Although gases are generally discussed in terms of pressure when studying kinetics, they can also be discussed in terms of molarity. And you can use other units too, like grams per second, essentially something that indicates some measure of chemical content per unit time. You don't necessarily have to use molar per second. There are two types of rate, average rate and instantaneous rate. The average rate is just sort of delta concentration over delta T. It's just measured at two different points in time. What was the average rate during a period of time? And then we have the instantaneous rate, which is you draw a tangent line on a graph to the time you want at the instantaneous rate. Alternatively, if you're given a line of best fit, you could differentiate it and take the derivative at that point, which is equivalent to saying the tangent line at that point. And consumption rates, production rates, and reaction rates can either all be instantaneous or averaged. Reactions generally tend to get slower over time, as we can see here on this graph. So the data, this dashed line here, so this is the reaction we were looking at before. This dashed line represents the average rate of reaction, or rate of consumption of nitrogen dioxide. Note how the nitrogen monoxide one is just a positive slope, and then note here how the oxygen one looks to be about a half as steep. It's shallower because of the reaction stoichiometry here. It looks to be about half the magnitude of the slope of this one. And then when we do the math here, it actually does turn out to be half, so it's 2 to 2 to 1, and the ratio is met. Essentially, the ideas here I want to get across is the idea of average versus instantaneous rate, the fact that reaction stoichiometries, basically you can do mole ratios with the rates as well, in addition to volume with gas and moles, obviously, since moles and rate are proportional to each other. And you can see that sort of in the graph here. And reactions typically slow down as they proceed. This is evident from the slope, and when we get to talking about the collision model, it will be pretty clear as to why that is. Yeah, there's nothing really else of content here, so we're going to move on to talking about the collision model. Let me zoom this in real quick. So we have seen that the concentration of reactant decreases, the reaction rate generally decreases. It's also been observed that chemical reactions speed up when the temperature is increased, or if the particle size of a solid reactant is decreased. And the model that we use to account for these observations is the collision model, which is the idea that molecules must collide to react with each other. So let's first talk about what exactly is the collision model. So let's draw some stuff out on some paper, and let's say we have a black dot and a brown dot. I'm not going to draw a bunch of them, I'm just going to draw one for the sake of explanation. And then let's say, okay, no, I want a black arrow. Let's say they collide into each other, right? And as a result of this collision, they will maybe stick to each other. They may form something like, no, that's not exactly the same color as we were talking about before. I don't think it makes a difference, but here. Let's say, and when they collide, they stick together. And this sort of thing happens all the time, where one collision will cause a chemical reaction, and the idea here is that the molecules have to bump into each other for something to happen. And if we go back here, we now consider three major things why a collision. So molecules must collide in order to react is the basic idea here. And some important things to note about this collision is that A, you must have the correct reactant particles for the collision to be successful. B, they must be in the correct orientation, like spatial arrangement. They can only collide if they're in a certain spatial arrangement relative to each other. And the last bit is that they must have sufficient kinetic energy in order to cause a reaction. Sure, you might have the first two bits, but if, say, for example, you're transferring an atom, you're transferring an atom between a pair of chemical species. If the other one doesn't collide at a fast enough rate, it won't be knocked off. The atom that you're transferring won't be, knocked off, and therefore nothing will happen. So that's sort of the idea of the collision model, is that you have to have successful chemical reactions you must have successful collisions for a chemical reaction to proceed, and the way you do that is you make sure that they're the correct reactant particles, you make sure they're oriented correctly, and they have sufficient kinetic energy for the reaction to occur. More on that third point. So there's quite a bit more on that third point of sufficient kinetic energy, and the first thing I want to mention here is activation energy, which Sponti-Arrhenius in 1880 proposed that molecules must contain energy greater than a certain energy threshold for a reaction to occur. So the activation energy is officially defined as the energy threshold that must be overcome for a chemical reaction to occur. This activation energy involves the energy required to break bonds from the reactants. So at higher temperatures, molecules are moving faster on average, so therefore more molecules can overcome the activation barrier. So if we consider this energy level diagram, here's the activation energy of the forward reaction, here's the activation energy of the reverse reaction. This is delta H, this is time, this is enthalpy or potential energy on this axis here, and you can do the same thing for an endothermic reaction. So the next thing I want to mention is the spread of kinetic energy at a given temperature given a set of molecules, and we represent this by using what is called a Maxwell Boltzmann energy distribution curve, which the temperature in Kelvin is a proportional measure to the average kinetic energy, as we discussed in topic 5. Well, I don't know. Well, I mentioned it earlier at some point, but for a particular sample of material at a particular temperature, since it's an average basically, not all molecules have that amount of kinetic energy. Some have more, some have less. And the way we can sort of represent the distribution of total energy within the system is by using a Maxwell-Boltzmann energy distribution curve at a given temperature. So this is what they look like, and you'll notice here is that the distribution is generally biased towards higher energy. Like you can see here that if we have like a normal bell curve, this and this should be, this side and this side should be equal. However, here it's clearly biased towards the tail end of the distribution. And on the y-axis we have the fraction of particles at the particular kinetic energy, and we have the kinetic energy of the particles on the x-axis. As the temperature increases, the curve more or less flattens, and the distribution shifts to higher energy. The average, the most probable, and the range of kinetic energy all increases. Note that the area under the curve is a function of population size, which does not change with temperature. So the area under the curve is just the number of the area under the curve is the total number of molecules with that particles with that given kinetic energy. So here we can see here for 3 different temperatures, we can see here is that this black line is 200, this dotted line is 300, and this dotted line is 500. And as we can see here, as we decrease the temperature, the curve gets flatter, and the spread of the curve is just wider, and the curves get wider and flatter. So that's sort of something to note there. Particles with energies exceeding the activation energy have sufficient energy to react upon properly oriented collisions. The area under the curve is representative of the population size, and a fraction of the area under the curve represents the fraction of the population size. So basically the area under the curve here, or the integral, if you really want to get technical, is representative of the number of particles that have a particular kinetic energy, or in this case the fraction of particles that meet or exceed the energy requirement. So as we can see here, we can mark down the activation energy since we know what that is numerically from whatever methods we are using. As when you get to the higher level stuff, we'll mention a way to measure it. And you can see here that this area under the curve is the total number of particles that will either meet or exceed the activation energy, and therefore when they collide with other molecules, have successful collisions to cause a chemical reaction to occur. At higher temperatures, since the energy activation is constant, as we increase the temperature here, right, this more particles have sufficient energy to overcome the activation barrier, and thus a larger fraction of particles will react as they collide. This intuitively makes sense because, if we increase the temperature, the particles should have more kinetic energy because they should be moving faster, and therefore, as a result, more of them should have successful collisions. And we can see that here on the Maxwell-Boltzmann distribution curve. Since the activation energy is always constant, if we change the temperature here, remember that the flatter curves means that the higher temperature, so T2 is greater than T1, we can see here that the area under T2 is much greater than the area under T1. In addition to increasing the temperature will just increase the number of collisions like per unit time, since the particles are moving faster, and therefore they can interact with more things in unit time. Since they move more, they go further. So that's also another thing too to consider. Lastly, we take a look at catalysts. A catalyst is something that speeds up a reaction without being consumed itself by providing an alternate route for a reaction which is associated with the lower activation energy. There's really not much more to it for catalysts. You just have to know what they are and what they do. So they lower the activation energy, so therefore here we have the activation energy with the catalyst versus without a catalyst. And since they're at the same temperature, the area under the curve is much greater with the catalyst than without, so there's that. Lastly, there's another thing I want to, I suppose, can talk about. It's not mentioned in the notes here, but decreasing the surface area, increasing the amount of total surface area will cause reactions to go faster, because collisions can really only happen on the surface of a material. So if you increase the surface area, you increase the total amount of area that can be, essentially, the amount of usable area. And as a result, for whatever reason, the IB loves to ask this sort of multiple choice question here. As a result, if you have the same mass, if you grind it up into small particulates, the smaller particulates will, react faster, since when you grind up something into smaller particulates, you increase the total surface area available, and as a result of increasing the total surface area available to a given system, um, you you increase the reaction rate, since there are more areas for collisions to happen, and therefore you increase the number of successful collisions per unit time. And yeah, with concentration, it's a little bit more obvious. You increase the number of particles within a given sample space, assuming the space is held constant. Since there's just more particles there, you can have more successful collisions per unit time, since there's just more particles in a system, that and therefore more of them have. There's a larger number with that meet the activation energy or greater, and yeah, sort of so on and so forth. That logic sort of builds on. So, what are the key ideas here with the collision model? You must have the correct molecules will bump into each other and collide with each other, and if they do so with enough kinetic energy in the right orientation, you will cause a chemical reaction to occur. That's really all there is to it. It's not a difficult model per se.